Thank you. Thank you, Julie. And thank you all for having me this afternoon. I feel kind of honored to be here. I'm going to actually start, I think, this presentation with a little bit of background so you kind of understand where this book came from and where this presentation came from. I actually my undergraduate degree in geology was from Michigan Technological University, which is up in the Upper Peninsula of Michigan. A place that'll always kind of be home and have a special place in my heart. But of course it was a secular geology training. And despite having grown up in the church, my family had been Lutheran. I always joked we were from Germany, so I thought we were Lutheran as far back as Martin Luther probably. But despite that, and despite growing up in the church, my interest in science kind of caused me to begin to ask a lot of questions. And for me, the reality that both things couldn't be true was very real. I realized pretty early on that if the earth was as old as all of that, then Genesis really didn't make sense. And initially it just started being a compartmentalization. I still went to church on Sunday, but that's kind of where faith was. It was my Sunday thing in the morning. And then the rest of the time it was, my studies and really quite honestly thinking something completely different from what I did on Sunday morning. Eventually that leads to just, well, now I'm not really going to church on Sunday mornings, and now I'm not really sure that God is really that important anymore. And maybe this just isn't the truth. And so that's pretty much how my life went. I met my husband. Together we kind of left the church and began to have children, and God kind of wanted to get my attention. And so we had some things happen during those years. I was told I wouldn't be able to have children. Eventually I did get pregnant. I was told that if I didn't terminate my pregnancy, I would die. That ended up not happening, and today the son that they said wouldn't survive that particular incident he's a 15-year-old that's 6'4", and as healthy as anybody you'd ever want to see. But God used that to sort of get my attention. Ended up still this struggle that I personally had though with old earth and what it said in Genesis, and it would take me actually a really long time to begin to put that together, much longer than just that incident with my son early in my marriage. And so this book actually arose out of kind of my personal faith journey of trying to piece that together. And it started when I decided to homeschool my children. I ordered a complete curriculum. And I had a 4 and a 5-year-old at the time, 4 and a 5-year-old boy. So of course, as I opened the box, the first book they pulled out was a book about dinosaurs. And it happened to be a book about dinosaurs that was published by Answers in Genesis. So they, Mom, read this book. I sit down with my 4 and 5-year-old on my lap and I start reading, and I would not lie to you. I shut the book. I said, this is nonsense. This can't be true. I know dinosaurs didn't walk the earth with you. I know that these things are not true. But what it began was this sort of journey of, well, maybe could it be? Maybe is there something that I didn't realize? And I'll be honest with you, I had never heard creation science. I didn't even know there was another explanation. How I made it to, my 20s and growing up in the church and just never even realizing, I'm not really sure. But it became sort of a personal faith journey. As part of that journey, I did begin to believe that there was actually quite a bit of evidence that Genesis was right. And maybe this wasn't such a far-fetched story after all. But the final step of my journey was really this book. What happened was at one point I set everything down, and I actually had a conversation with God that went something like, if all of this is true, then I ought to be able to explain what's outside my back door to my kids. It's fine if I can go explain the Grand Canyon. It's fine if I can find a book that explains Mount St. Helens. But if I can't go on the hiking trail that's only an hour from my house to the top of Rib Mountain and explain to my kids what I see there as well as I can in an old earth uniformitarian paradigm, then I can't really believe that this is true. And so that's where the book started. Really, it was just about me being able to explain it to my kids. I had some people come into my life that encouraged me to make it available to other people and things along the way, but this truly is just my faith journey and part of my story. And so I share with you because I love geology, and some of these places are pretty cool. You should go see them. And in the beginning here, I would say that the geology of Wisconsin, we're pretty much going to start with the flood. So what happened before the flood in the beginning? We know there's some evidence that things were probably quite different. A lot of gigantism. I love the dragonflies with 2-foot wings, and the reason I include them is because I always wonder what our mosquito situation would be today if we could have hung on to the dragonfly with the 2-foot wing, But the longevity of humanity, there's a lot we don't know, but clearly something was different pre-flood. The way I set the book up is I picked some state parks in Wisconsin, and I decided to put them in chronologically instead of geographically. So if you were to buy a copy of my book and go from site to site, you'd spend an awful lot of miles in gas zigzagging, because it is chronological, not geographical as far as the tour goes. But I begin in northern Wisconsin, and for those of you, that we do the mitten in Michigan, right? You always use your hand. But this is really in the center of Wisconsin, about an hour south of Lake Superior, and it's part of the Lake Superior watershed. And so I'm just going to kind of tell you a story of how the flood impacted the geology of Wisconsin. And once in a while, I'll throw in a place in Minnesota, the few places I know, and as I'm here longer, hopefully I'll begin to add some Minnesota sites to the tour as well. Copper Falls State Park is in the middle of what's called the Mid-Continental Rift System. And this is the fountains of the Great Deep breaking open. So as you've had a lot of amazing speakers here, you know that the Bible talks about that before the rain. And we think that that's the rifting of the plates, the breaking up of the earth into those plates. And we still see the rift, or you can see it almost like a scar through the Earth's oceans. Well, the same kind of rift started to form in North America. And this rift actually goes all the way into Kansas, and it kind of swoops around and goes down into Michigan. In most places, you can't actually see the rift because it's buried in either flood sediment or ice age sediment. But in the Lake Superior Basin, it's very visible. And so the continent was tearing apart here. And the same way that it tore apart to form the ocean basins like the Atlantic Ocean, this would have put great and tremendous quantities of basalt, or kind of the mantle material, onto the Earth's crust. And basalt's a pretty dense, heavy rock, so it starts to kind of sink. The Earth's crust is a little bit of rebound there, and as more basalt is erupted, actually some of the thickest basalt lava flows in the world are in the Upper Peninsula of Michigan. And I have a picture of one in just a little bit, but you're also going to have volcanoes associated with that are erupting rhyolites on top. So in this rift in the Lake Superior region and in Copper Falls State Park, you begin to see all of this volcanic rock layered up. And as the crust started to downdrop underneath the weight of this new material, it actually forms, it starts to fault and form a graben, kind of a downdropped area in the Lake Superior Basin area. So Lake Superior actually existed before the Ice Age. A lot of the Great Lakes, I know a lot of my high school students will think they formed during the Ice Age, but there was actually already a depression or a graben here in Lake Superior prior to the Ice Age. The Ice Age kind of gave us the final shape, but that wasn't the initial beginning of Lake Superior. And so you get these volcanic rocks, you get this downdropping, and at the same time we have rain just pouring down. And that's also going to result in a lot of weathering and erosion. So in addition to all of these volcanics that are filling this downdrop graben, now you have all kinds of sedimentary deposition. Excuse me. And you can see here, this is actually my 15-year-old, the one that's 6'4" now, obviously a few years earlier, but he's standing on the Copper Harbor conglomerate, which would be some of that rift-filling sediment. So a lot of the clasts, a lot of the bigger rocks inside of that conglomerate are those volcanics that are now eroding as the rain and some of that torrential downpour is happening as the flood continues to go on. The sediments in Copper Falls State Park are going to be a little different than some of them that we're going to see as we keep moving through the state parks because they're very local extent. So that tells us that the flood didn't cover this part of Wisconsin as this is forming. The floodwaters aren't already covering the entire continent. Because there's local extent, there's no fossils, a lot of the clasts are right from the volcanics. So this is all kind of happening in one event, one catastrophic eruption. And this is Cliff Drive in the UP, if has anybody ever been to Houghton, Michigan, or the Copper Harbor area? So this is Cliff Drive. If you go to school at Michigan Tech, you're sure to get the opportunity to rappel and climb up and down this cliff. But this is one of the thickest lava flows in the world. So this is one of those giant basalt lava flows. We also have some evidence here of the rapid cooling that would have happened. So in Copper Harbor and in the UP we have a lot of these amygdaloidal basalts. And I just like to use that word because I think it's a good dinner table word, especially for my high school kids. I always tell them, here's one to use at the table tonight with mom and dad. But it just means there's a lot of holes in the rock. So it's almost like opening your soda can and the bubbles start to escape. Well, it's a similar thing. The gases that were trapped in these lavas once they were erupted on the surface, as those gases escape and it's cooling rapidly, you have a lot of these vesicles or holes left behind in the rock. All right? And then if we go back to this whole idea of the fountains of the great deep, the waters that are actually coming up from the Earth's mantle are going to have a lot of minerals in them, a lot of dissolved minerals. And as they cool, flowing through these lava flows and through these rocks, a lot of those minerals will precipitate out. So the reason it's called copper country, of course, was because of all the copper deposits in this part of Michigan, and that's where a lot of those would have come from. They precipitated out of solution into vesicles and cracks that formed as this lava was cooling quickly on the Earth's surface. Copper Falls State Park, though, doesn't have copper, by the way, so they looked for it. They do find other minerals, and this would be a similar formation mechanism for the Lake Superior agate as well. So another popular pastime. I know you do it in Michigan on the North, or Minnesota on the North Shore too, right? Looking for the Lake Superior agates, and that would have a similar formation. Okay, you're going to have these hydrothermal fluids, or these waters from the deep. Now, one of the interesting things is sometimes secular science discovers things that support these types of ideas. And one of the recent things that's come out in Nature and some of the other science magazines is that there's an ocean worth of water still today in the Earth's mantle. So to give the mantle as a source for floodwaters is not a jump or an unrealistic idea. Oh, did I skip one? Now, Rib Mountain's special to me. You heard me talk about it a little bit at the beginning. Rib Mountain was actually what started this whole project. So this was just only about an hour south of my home in Minnesota, or in Wisconsin, and it was a place I took my kids often, and I could not explain it. Actually, I started writing this book. I could explain almost every place that I wanted to explain, and I still could not explain Rib Mountain. And so I have a debt to Michael Ord and Dr. Clary, a couple of people that were willing to take some time to really try to help me understand what was going on at Rib Mountain. But Rib Mountain is the highest relief in Wisconsin. So if I had, I like to call on, the high school and middle school kids, because as a teacher, that's what I like to do, but they sat way in the back, so I couldn't call on them. But the difference between relief and elevation, of course, is just where the ground is, as opposed to above sea level. So Rib Mountain's not the highest elevation in Wisconsin, but it is the highest relief. So it's a very obvious feature on the landscape. And it's quartzite. And it's quartzite with ripple marks. Now the reason that's kind of interesting is because if you've ever walked on a beach, how long do ripple marks last? And you've probably had speakers talk about this, but they don't tend to hang around for a real long time, do they? Usually not long enough for the sand to turn into rock and lithify. But this is actually a metamorphic rock. So this isn't just ripple marks in a sandstone. This is ripple marks in a metamorphic rock. And the way you change a sedimentary rock like sandstone into a metamorphic rock like quartzite is heat and pressure. So one of the questions I had is, how in the world do you preserve something like a ripple mark, which is difficult to preserve anyway, in a metamorphic rock that requires heat and pressure to preserve it? And that's not the only feature that you see. There's cross-bedding in the rocks in Rib Mountain. You can still see the bedding planes from the originally deposited sandstone. And the sandstone that makes up the quartzite, or that became the quartzite, is pure quartz. And it's very uniform. The grain sizes are 90 to 95% the same. The reason that that's interesting is because that tells us it was transported a long distance in order for so it's not just a big mix of things similar to what we saw in the rift, where things were dumped into the rift and we've got large class and small class and sand and silt and mud. This is a 90 to 95% pure sandstone that changed into a quartzite. And so even in the secular science, trying to explain Rib Mountain is a little bit tricky, which is what I also discovered. It's not quite straightforward no matter how you look at it. But they said, well, it's really difficult to come up with a legitimate way to get these quartzites into Wisconsin. And I think the flood actually provides us with actually a great method, because at the same time that we have this rifting going on to the north, we have the floodwaters now starting to advance on the continent. So that rifting was happening at the beginning. Now we have tsunami-like waves that would have the capability of bringing some of these well-sorted sediments from a distance that are beginning to wash onto the continent in these tsunami-like waves. And they're going to start to fill low-lying areas that are on the existing continent. As they do that, in the Rib Mountain area, we have a lot of igneous intrusions. So the crust is starting to melt, all right? And we have all of these intrusive igneous rocks, this magma pushing up below these quartzite, or sandstone initially, deposits. The heat from these intrusions with the quartzite on top might provide a mechanism for almost instantly metamorphosing these sandstones into metamorphic rock that would allow them to retain these sedimentary features in a way that you wouldn't have if you just waited for long periods of time and tried to retain this kind of fragile structure over those periods of time. The Wausau area is actually pretty well known for these igneous intrusions. The Wausau red granite is used in a lot of headstones. So if you travel around the state, I imagine even in these states, a lot of the headstones that are granite are made of this Wausau red granite. There's something called a rotten granite. That's a lot of the gravel you find on the roadsides. It's very easily weathered. But all of these different intrusions have different chemical compositions. And that's because they came up at different points in this process. The quartzite over top of one of these intrusions, the Rib Mountain quartzite, is actually over a quartz syenite intrusion. Quartz syenite has a relatively low melting point, and it's lower than the quartzite. So that would allow the quartzite to stay brittle as the molten syenite was intruded below it. And the way that Rib Mountain ended up where it ended up is this quartzite layer actually was pushed up by the intrusion. It broke, and the entire layer rotated 90 degrees in the quartz syenite intrusion. And so today, it's almost vertical. Ripple marks that were originally deposited in a horizontal orientation are vertical at the top of Rib Mountain because the whole thing actually behaved in a brittle fashion and rotated within the syenite intrusion that later cooled. So what are some reasons or some evidences? If you talked about the secular explanation for Rib Mountain, it would be very similar as far as the actual rotation of the quartzite. But why do I pair this with the mid-ocean ridge? They would say that this is part of the roots of an ancient volcanic chain that happened significantly earlier than the mid-continental rifting system. They wouldn't put those two together and relate them. But there are a couple of pretty strong evidences that actually they should be related. One of them is that the intrusions here are actually a type A igneous intrusion that are often associated with continental rifting, not with the roots of ancient volcanic chains. So in other words, the minerals that are in these igneous intrusions would fit better with a rifting event than the roots of an ancient volcanic mountain chain. Now, we all know that there's a lot of things, and I think your speaker next week is going to talk about carbon-14. So we know that there's issues with radiometric dating, but to the extent that it might be useful for relative dating, the dates on these actually match the mid-continental rift system when they do the radiometric dating. What secular scientists say, they say that there was an unspecified regional thermal event that reset the clock. And so that's how the rocks get older. But I don't think that an unspecified regional thermal event provides a better explanation than just maybe that they are related to each other in time and space. It's also pillow lavas in this area. Pillow lavas are basalts that are erupted into water. You would find these in places like Hawaii. So more evidence that now the water is becoming, or coming onto the continent, that the continent is experiencing more flood-like conditions. And then there are radiohalos in a lot of the zircon crystals, especially within the rotten granites. And so what's going on here is essentially minerals are experiencing radioactive decay, and it's cooling so quickly that the halo that is evidence of that is being preserved in the crystals, which is pretty incredible. And And they've done a lot of writing about how this would happen in the presence of large quantities of water. That would help quickly cool these large intrusive or igneous intrusive bodies. So if you have a lot of molten rock underground, you would think it wouldn't cool very quickly, but in the presence of water, they've been able to model this rapid cooling, and these radio halos are evidence of that. So Rib Mountain turns out to be a pretty cool place, but it took me a long time to get there. But still a favorite, like I said. And that's just about an hour south. So far we haven't gone too far afield geographically either in our tour. Copper Falls, about an hour, 2 hours north of Rib Mountain. So that would be a day trip. You could probably make it work. Pictured rocks, we move into the Upper Peninsula of Michigan, and this is on the shore, the south shore of Lake Superior. This is when we begin to get into some more significant flood deposition of sediment. So if you head to the east side of the park, you're going to be able to see the last of those rift fill sediments. There's something called the Jacobsville sandstone. There's a lot of crossbeds, large crossbeds in it, which tells us that there was some pretty rapid currents during the deposition of that sandstone. But that is still local extent. There's still no fossils, and it's still primarily made up of material that came right from that rift system itself. But on top of that, we start to get the Chapel Hill sandstone and the Miners Castle sandstone. And these would be part of the first megasequence that would have a continental extent. So we call it the Sauk megasequence. This was one of the gifts that petroleum engineers have given us. In their quest for oil and gas, they've done an awful lot of drilling, and what they discovered is that there are actually sedimentary sequences that extend across the entire North American continent. And this is another great evidence for a global flood, because how else do you get something with deposition across an entire continent with a continental extent? And interestingly enough, and I think that, I'm not sure how much of it is published yet, but I know ICR is doing a big project right now looking not only at the extent in North America, but they're moving into Africa and saying, we can match these things in Africa and South America, and so we're talking really about global extent. And so here at Pictured Rocks, you can see the earliest sequence, right? And here we start to get sedimentary layers that aren't just local. Again, a lot of cross-bedding, a lot of these, I'll take a step back here. So this is happening a little bit to the east of the rift. And the reason we're starting to see sediment here that we don't see in the rift is the rift kind of became the thing everything else had to go around. We have a lot of igneous rocks coming up here. And so this is where we're seeing the earliest of the flood sediments. And these megasequences will be deposited then, thinning away from the rift. So the closer you are to the rift, the thinner the flood sediments, because they're actually going around this rift. And here you can see, I'm not a great photographer. And so like I said, this started as a personal project. If I was going to do it again, I'd probably go back with somebody a little more skilled. But if you can see the crossbeds here, you know, one of the things, the larger the crossbed, the faster the currents had to be. They've done a lot of studies with this. Berholt has done a lot of studies looking at the velocities that you would need to have crossbedding, ripple marks, thin laminated bedding, and those are all related to the speed of those currents as those floodwaters begin to wash onto the continent and move across it. I should mention before we leave Pictured Rocks that the reason it's called Pictured Rocks is because the cliffs are painted with colors. And again, that's going to be as the flood retreats, leaves the area, as some of those waters, those hydrothermal fluids, a lot of that mineral-rich water begins to move out of the sediment as it's solidifying, it's going to precipitate all of those pretty colors on the fronts of the cliffs. So you get the reds with the irons and some of the green because we know there's some copper minerals up there and things like that. So the Pictured Rocks still are fed by rainwater. In the years of the Ice Age, those colors would have been fed by meltwater from the glaciers. From there, we're actually going to move closer to Minnesota, and we'll get over here to the west side of Wisconsin and Perrot State Park. One of the things that happened in Wisconsin, and in a lot of Minnesota too, is that we don't see a lot of the megasequences beyond the Sauk megasequence, which was the first one laid down, because a lot of it here was eroded during the retreating floodwater stages, and then of course the Ice Age and the meltwaters from the Ice Age and a lot of glacial things cover much of what we can see here. But we can find some of these features in Perrot State Park because it's in what's called the driftless area. The driftless area just means that the glacial ice didn't reach this part of Wisconsin. And it goes into Minnesota too, so this is a place where Minnesota too is part of this driftless area where the glaciers never came. And so again, we can see as you hike up Brady Bluff, and this is a picture as you hike up Brady Bluff, again, you're gonna see these fining up sequences. You start with a basal conglomerate, you move into sandstones, so gradually the particle size gets smaller. That was one of the things that I struggled with a little bit too. How does that happen if you don't have time for particles to fall out at different rates, different depths, different depositions? But Guy Berholt also did those experiments and discovered that this can be done really very quickly. And we've seen that now with some of the hurricanes. Hurricane Carla deposited things quickly, and we see the exact same fining upward sequence that we see in a lot of these sediments deposited by the flood. So there is some recent evidence that these things can happen very quickly and don't take long periods of time. Actually, I'm going to go back to the first picture because this is kind of where we start to turn and talk a little bit about the end of the flood. So we're going to continue to deposit megasequences one on top of another. And then as the floodwaters run off, we begin to make drainage channels like the Mississippi River here. So at the top of Brady's Bluff, you can begin to see some of the drainage pattern from the Mississippi River as the floodwaters would retreat from the continent in this area. Even though it's in the driftless area, the glaciers did affect this because later on when the glaciers would melt, floodwaters, specifically from glacial Lake Duluth, would run through those same channels to deepen them, to change their shape. So much like Lake Superior's final shape was kind of determined by the Ice Age, even though it was already there from the breaking open. Similar things with this driftless, or the channels of the Mississippi River here in Perrot State Park. The final shape is actually the result of some of the glacial melting and glacial activity, but it began with the retreating floodwaters. I like to talk a little bit about the driftless area just because I think the driftless area is another interesting evidence for a young Earth. Just the fact that we have an area that the glaciers never touched. So I know there one time, if you went to one of these parks, it would talk about the 4 major advances into Wisconsin. Some people will say there were up to as many as 30 ice ages in Wisconsin. And so the fact that we have a driftless area that didn't have glacial ice, why would in multiple advances and retreats? There are some highlands, we have the rift system, we have some things that glacial ice might move around, but why would we move the same pattern over and over and over through multiple advances? Would that topography be the same every single time? So having a driftless area speaks to more of a single ice age scenario rather than the repeated ice ages. The other thing is that ice ages really aren't that easy to come up with a mechanism to have an ice age. So in order to have an ice age, you have to have an increase in precipitation and cooler than normal temperatures, especially in the summer. But we all know in the winter what happens when it gets really cold to your throat and your nose and your eyes, right? And we all have to put on extra lotion because cold air is dry air. So to bring those two things together is not as easy as it might sound. And so a lot of explanations will do one, but fail to really account for the other. Yeah, we can account for increased precipitation, but not at the same time as cooler than normal temperatures. Or we can account for cooler than normal temperatures by talking about cycles and the Earth's rotation, but how does that give us the increased precipitation and humidity that we need? But if you have the fountains of the Great Deep bursting open in the Earth's oceans, you have molten material entering those systems and heating the Earth's oceans, you're going to get higher rates of evaporation that then move over the continents. At the same time, with all of the volcanic eruption, you're putting a lot of volcanic ash into the air, which reflects the Earth's sunlight away. So you're also going to get cooling temperatures. It's one of the mechanisms that could actually explain that those two things that don't really seem that they should go together, or maybe don't normally go together. And so again, if you're going to have 30 ice ages, you have to come up with a mechanism to do that repeatedly. And that's kind of the same thing in Perrot State Park with the mega sequences and the multiple layers. A lot of times the geologic explanation that I learned, at least in college, was that the Earth's crust continually rebounded and sunk and rebounded as the oceans would advance and retreat and advance and retreat. So you'd have oceans come into Wisconsin, and then they'd be gone again, and then they'd come back. Well, again, you have to account for what mechanism causes that kind of continual cycle to happen over and over again. From there, I moved back to the Upper Peninsula. So like I said, this isn't geographically your best route. But we're going to go to Peninsula Point, and this one's my favorite, and it would be very different than any of the places that we've journeyed so far in this tour. If you walked out of your car here, you'd wonder why I even took you here, because you wouldn't see much other than Lake Michigan. But this is a beautiful, beautiful park in the Upper Peninsula of Michigan. You can only get there on a one-way dirt two-track, so you have to be prepared with the appropriate vehicle to get here, but it is very much worth it. This lighthouse is open to the public, and in true Upper Peninsula of Michigan style, there is no park ranger, there is no admission, there's no lines. You can walk in the building, climb the stairs, and you can enjoy the top of that tower. And I just think that's one of the most unique and interesting features of the park, because too often there's a lot between us and the experience. Here that's not the case, maybe except for the difficulty in getting there in the first place. Yeah. But if you walk out here on these rocks, what you'll discover is a fossil graveyard. There's fossil upon fossil upon fossil, one on top of another. And you can collect them. Kids love it. But you have to get right down by the lake, so you can't see it until you get down there. Fossil graveyards, it's kind of like ice ages. You know, it's easy to say, well, there were 30 ice ages and that explains it, or the oceans came and went all these times, but how do we explain fossils? Fossilization doesn't happen today. It's not that easy. What happens when, you know, you I give away, but I hit a pheasant on my way to work the other day. Well, he's not going to stay there until he becomes a fossil, right? He'll decay. Fossilization isn't easy. So how do we explain the abundance of fossils in the fossil record? And the abundance of fossils everywhere, not just in a certain location. It's not just in the Upper Peninsula of Michigan. Although this is one of my favorite places to look, there's fossils everywhere. And interestingly enough, and it's not part of this guide or this slideshow because it's not open to the public, but in the center of Wisconsin, in Mosinee, not too far from Rib Mountain, there's actually a jellyfish fossil graveyard. Jellyfish have no hard parts. The only way to fossilize, you know, this huge amount of jellyfish would be catastrophic burial, and instantaneous fossilization. And so just the fact that we have so many fossils speaks to rapid burial. The signs in this park will say that it's a reef that was fossilized. Again, reef systems, that's another thing that's often brought up. Well, it takes a long time to build a reef system. But the types of organisms, the crinoids, the brachiopods, some of the things that we find in this particular fossil graveyard at Peninsula Point, Steve Austin has done some writing on this in suggesting that this is a more loosely bound organic kind of reef. It's not the coral reef we think of when we think of, for example, the Great Barrier Reef in Australia. That's not the kind of animals we're talking about in these types of reef systems. So just a really great place. The other thing that's really neat about this park, I'm just going to put my pitch in for anybody that wants to go there. Huge open grassy areas. Great place for wiffle ball games with your kids. Picnics. It's a neat spot. And now I couldn't take you much farther from there on the road than to take you back to Cave of the Mounds in southern Wisconsin. But we need to talk a little bit about cave systems because, of course, that's also one of the difficult things to explain, right? Caves take forever to form, and it takes a long time to make stalactites and stalagmites. So how do we look at something like this and explain it? So Cave of the Mounds in southern Wisconsin is going to represent part of the end of the flood year, too. So as the waters begin to regress, they're flowing off the continents, you're going to get some crustal rebound, some uplift, and that's going to cause some compression in the sediments that have been laid down. And as that water flows out, especially in those limestone sediments, you're going to get the dissolving of the limestones and those waters carving out these holes. I think you have quite a bit of karst topography in southern Minnesota too, don't you? So this would be a similar scenario. And of course, in southern Wisconsin, there's also some mining that goes on there. Things like zinc is mined in southern Wisconsin. So what that means is we probably have some sulfuric acid in the system. So with these hydrothermal fluids, we're not relying just on, for example, carbon dioxide from rainwater to begin to create these large caverns. After the caverns are hollowed out, then meltwater from the glaciers and increased precipitation post-flood would allow for the formation of these stalactites and these stalagmites. And again, we've seen these happen in relatively short time periods. Some of the caves you can actually see, somebody went down and left a bucket and it's already beginning to form some of these features around it. An interesting thing it's interesting sometimes when somebody asks you a question that you've never thought about and you wonder why you never thought about it that way before. But somebody asked, well, if you were going to form a stalactite or a stalagmite over thousands and thousands of years, do you realize you'd have to have the same drip point? So the topography on the surface where the water is coming down into the cave would have to remain constant for those thousands of years. And we're talking about a state that went through an ice age. How would the topography on the surface stay the same for thousands of years so you would have this constant drip point to allow that stalactite to form over long periods of time? And for me, that was one of those, why did it never occur to me before that you'd have to have that constant source? Maybe I shouldn't admit that. That's probably something I should have thought of. I also included Kitchatipi because, and it's also known as Palm Book State Park. This is in Michigan. So if you didn't want to go all the way back to southern Wisconsin, you can find karst in the Upper Peninsula of Michigan. These are some really cool natural springs at the bottom of a sinkhole. So this time you have something similar to Cave of the Mounds in that you have this hollowed out structure, but here we don't have the roof because it's collapsed. You can see the sand come up from the bottom of the hole and paint pictures on the floor of it. But there's still sulfuric acid in this particular spring. So you'll see that on the signs when you travel there. Again, it's just another really cool spot because being the Upper Peninsula of Michigan, you can just hop on this barge. And again, there's not anybody to necessarily stand between you and your experience. There's a little wheel, some ropes across, and you take yourself right out into the middle of the lake on the glass bottom barge. You can enjoy the experience as long as you want because you self-pilot your raft. And so just another plug for any time you can get close to an experience with fewer things in between you and that experience, it's always worth the trip. So just another really neat park in the Upper Peninsula of Michigan. And then the final stop, well, not quite the final stop, but in the chronology, this will be the last stop in the chronology, and then I have sort of a state park that brings everything together. But of course, the most significant features we see in Wisconsin and also in Minnesota here are features from the Ice Age. And we talked a little bit already about the flood creating the perfect conditions for the Ice Age. So conditions where we would have had increased evaporation in the Earth's warming oceans or warm oceans from the breaking open of the fountains of the Great Deep. We've got cooling temperatures because we have volcanic ash in the atmosphere now, reflecting sunlight away from the Earth. And so we did have glaciers that advanced down into Wisconsin and Minnesota, and they really significantly changed the landscape. This is why a lot of flood sediment you can't see. A lot of that would have been eroded by the large glaciers coming down. Even the places the glaciers didn't actually reach, so as you get further south or into the driftless area, those areas were still impacted by meltwater that came down, especially, like I said, in places like Perrot State Park or the driftless area. You had Glacial Lake Duluth that would drain through there with some of the meltwater. Kettle Moraine State Park, I point out just a couple of my favorite features. Drumlins are a great one. So for a long time we didn't understand how drumlins form, and I don't think we still understand exactly how drumlins form. But they're kind of a teardrop-shaped feature on the land. They have one steep side, the other side kind of is more gradually sloping. And actually in Minnesota, near where I live now in Perham, there's the Wadena drumlin field that just has thousands and thousands of these drumlins. Well, just recently, they've seen these things actually forming in Iceland. So when I did my undergrad degree a million years ago, they thought maybe there was something that the glacier kind of ran into and it pushed up and then it dug back down on the other side. But now they see these things forming in Iceland, and they see them forming under relatively thin, fast-moving ice. And so in one of the secular scientists or science journals, the scientists have actually said if this is true, it suggests that the glaciers moved much more rapidly than we thought. So these seem to be a feature that indicate relatively thin ice moving relatively rapidly. So if you look, for example, in Wadena, where we have thousands of these, if any of you have driven 210 on the west side of the state, you just go up one and down the other. It's almost like riding a roller coaster, because it's up one drumlin and down the other, up one drumlin and down the other. And just we have some great features in this state, from Kettle Lakes. Why is Minnesota the land of 10,000 lakes, right? Because a lot of this glacial sediment, some of these ice chunks that broke off the glacier became embedded, they melted, they formed these kettle lakes. It also happened in the meltwater areas, so the outwash plains in front. Same in Wisconsin. A lot of the small lakes in Wisconsin are kettle lakes. Cames, there's a lot of cames in Minnesota. I think even more than I saw when I lived in Wisconsin. We were at Maplewood State Park last week, and we climbed to the top of one that's on the Alexandria Marine Complex. These nice conical shaped hills, they were actually lakes on the surface of the glacier, and then as volcanic ash and sediment filled the bottom of the lake, just like it would a lake on the surface today. But when the ice melts, that deposition in the bottom of what was a lake on a glacier becomes a positive feature on the landscape as it melts. Eskers are similar. Rivers on the surface of the glacier, you'll get accumulation of ash and other sediment in those river structures, and when the glacier melts, you end up with these hills that look like rivers, except in positive relief rather than in negative relief. And so you can find a lot of these things in both Minnesota and Wisconsin, but especially in Kettle Moraine State Park. All right. And so that's kind of how, for me, I was able to put together, and again, a lot of this geology was done by incredible creation geologists that really helped me see the possibilities. And then I said, how can this apply to the place where I live now? And so that's sort of the flood year in Wisconsin. And I always like to finish with Devil's Lake, because you can see absolutely everything in one site. So if you can't go to all 8 places, or you can't do the entire tour of Wisconsin and the Upper Peninsula of Michigan, you could see most of this just by going to Devil's Lake State Park, which is in the Baraboo area, a little bit north and west of Madison in Wisconsin. And here we have I hit the wrong button, sorry. I need more practice. Here we have quartzite just like we had at Rib Mountain. So Baraboo quartzite was formed in a very similar way, except in Baraboo, the intrusion had a little bit of a higher melting point, so there the quartzite behaved in more of a pliable fashion. It folded, it created a big fold rather than behaving in a brittle fashion and actually breaking and rotating in the syenite intrusion. So here we have big folded limbs, and those are going to block up 2 sides of Devil's Lake. So on both sides you have the Baraboo quartzite cliffs. In Parfrey's Glen, we have a lot of the flood sediments. So this is some of that conglomerate. Here it's sometimes called pudding stone. And in Parfrey's Glen, you'll actually find clasts or boulders within the conglomerate that are enormous, and they're made of this Baraboo quartzite, which is an incredibly difficult rock to erode and break down. And so no matter who you talk to, no matter what their view of the age of the earth is, all geologists would say that this had to be a catastrophic deposit, because you have these enormous, they call it pudding stone, just enormous boulders and clasts of quartzite that have been embedded into this conglomerate in Parfrey's Glen. So we can see some of the destructive power of a global flood here. And then the Ice Age also impacted. So I mentioned that the folded arms of this quartzite fold blocked 2 limbs of the lake. As the glaciers came down, they pushed a moraine in front of them, almost like a bulldozer. A big pile of glacial till or a big moraine blocked one end of the lake on the other side. And then they had to go around the quartzite cliffs because they are very erosion resistant, and they pushed another moraine in the backside. And so that's how you get Devil's Lake. It's a lake above sea level by quite a bit. Two sides it's dammed in by the Baraboo Quartzite, the other two by moraines from the Ice Age. So you can see kind of an overview of the whole chronology if you want to just head to Devil's Lake for an afternoon. Also just a neat spot to go. All right, so this was sort of my quote for myself. You know, it's easy to, sometimes it's easy to ignore the evidence right in front of you, but ultimately I think it comes down to trusting God's word and believing that God's word is true. And when you start from there, instead of, you know, for me, especially I think when I was young and looking at science, I was always trying to prove that God existed. I would start with science and prove he existed. And to a certain extent, I think even this book, you know, I had to prove to myself that God existed. And what I ended up discovering was that that's the wrong starting point anyway. I start with God, and then I let the rest of it make sense. So thank you guys for having me. I appreciate the chance to tell my story. And you're going to talk?
What is it like to be on a tour with you and your family? Going to a state park and you have a geologist who's talking about how millions and millions of years old this is and that sort of thing. How do you approach that and
what does that look like? Yeah, it's been interesting. First of all, when I'm talking, it's not uncommon for people to come, start to listen and ask questions, which I always think is good. When we're on a tour with someone else, I don't know if I've ever done a geology tour for my kids, but I know we went to an aquarium once and we were talking about sharks, and they were like, which evolved first, the shark with 5 gills or 4 gills? And we got, my kids said, well, they were created on the same day. Like, what do you mean, which came first? So there are those moments, and I guess it's opportunities to speak. I'm not an expert. You have some amazing experts that come here and speak, and I would say that I'm still a learner in many ways. So I always enjoy asking questions too. Ask them, why? Why do you think this? What evidence convinces you of that? And you can learn a lot, I think, just from having that dialogue as well. Yeah?
How long is your ice age that you described, and how is it dated?
Relatively short. I know Michael Ord would say in about 500 years after the flood that we would have hit the maximum extent of the ice age, and that it could have left the area in about 200 years. So that would be a significantly shorter time frame than you would find in most secular accounts. However, like I said, some of this new evidence coming out, and this is evidence from Iceland and some of the work they're doing there, would suggest that the glaciers did probably move more quickly than the original estimates.
And just so you know, I used to be a naturalist at Devil's Lake. And
oh, awesome.
We didn't say that it was 30 different ice ages. We said it was 30 different advances and retreats of ice.
Right. I'm sorry.
Now I feel better.
I do feel better.
So we wouldn't say something dumb like that.
Well, my understanding was 4 advances in Wisconsin. When I say 30 different ice ages, I'm actually talking more about globally and the evidence from the Greenland cores rather than specifically Wisconsin. So I should have been clearer too. Because yeah, in Wisconsin it's the major advances. But I think that 30 and sometimes even more comes out of some of that Greenland work that they've done. In Parfrey's Glen? So Devil's Lake, the cliffs are, Copper Falls. Copper Falls. All right, I'm sorry. Yeah, the main part of the rift is volcanics. So it's basalt and rhyolite. Rhyolite would be surface eruptions. Basalt is what would have come out of the rift from the magma or the Earth's layer under the crust. The conglomerates there are actually going to be rift-fill sediments that come in after or during. There are some in between the layers of the volcanics, but a lot of the rift fill sediments came in after and filled in kind of that crack. So now you have a lot of the flood rains coming. Not complete flood coverage, but you have a lot of weathering from rain. And so it's going to be a sedimentary feature, a lot like a lot of the flood. You're going to get a lot of that, especially the initial conglomerate, a lot of the big pieces in there, and then you get layers and layers on top, and especially if you're looking at like an entire flood where you're getting these sequences rapidly, then they're going to lithify and turn to rock as they're buried by other sediment.
Is where the river flows and all that, is that where the rift is?
In Lake Superior?
No, in Copper Falls.
Yeah, the river flows through and over some of those lava flows. So it's not, the rift is actually in Lake Superior, but these volcanic layers, as they erupted onto the surface, they called kind of a down warping of the crust. So they're at an angle now. They're not horizontal anymore. And then there was actually some faulting. So as they're down warping, there's cracks and it kind of down drops. And later, it becomes a horst. There's some other compression things that cause it to uplift. But the layers now are at an angle. So the falls actually go over some of those plains. There's actually a couple falls there. So some of them flow along and some of them flow over. There's two different directions, Brownstone Falls and Copper Falls there.
Just two questions. The first one is, how do the stalactites form?
That's going to be, in some ways, it's almost similar to when I was talking about minerals precipitating out, for example, in the cracks in the holes. With stalactite formation, if you have minerals dissolved in water and they begin to drip, you're getting precipitation of calcite or whatever, the mineral that is making up that. Calcite is pretty common because of the limestone it's dissolving in.
Kind of like an isotope.
Yep.
Okay. And then just with your schooling, are you able to bring your biblical understanding into the schooling, or is it?
My understanding in my current work? The school that I'm teaching geology at currently is a seminary, and I teach in an undergraduate program, so they do know my views. I tend to, especially when I work with undergrads, I tend to present both sides because I actually believe that the evidence supports the young Earth view. But at that age, I'm asking them to begin to think critically, and I want them to make their own decisions. So I don't present one side exclusively in my classes, nor do I require my students to subscribe to what I believe. But that doesn't mean that I won't challenge and ask them to think about things. And, well, what do you think about this? Well, make sure you have a good argument for this. And that's the age of the student. I think that's what needs to happen at that particular age.
Yeah, your talk about cave development. I just finished reading my Answers magazine. And they had something. I just finished reading it yesterday. It says something about stuff coming up and forming the caves almost instantly.
Yeah, and I'm going to be honest. Cave development is a little bit out of my wheelhouse. But I know that, like, for example, in Carlsbad Cavern, wherever you have sulfur as part of the system, you get cave formation much more rapidly. So I know at Carlsbad, they've actually had to change the sign a couple of times. And now they've just taken the time of formation off the sign entirely. So there are interesting things happening, I always think.
So before you went from millions of years to thousands of years, do you believe that the layers of the earth built up over millions of years, or was it sedimentation, or?
Yeah, well, and of course, because I went to a school in the Lake Superior area, Lake Superior geology was a lot of what we did, and that was the transgressive and regressive sequences. So it was the advance of an ocean onto the continent. It stays for a while until you get, as the ocean deepens, you get finer and finer sediment settling out until finally you get the limestones and dolomites, and those take a long time to come. And then it it regresses and it's off the continent for a while, and then it comes back and deposits the next sequence. So that was definitely my understanding of that geology. Again, in a little bit in the way of why didn't it ever occur to me that you'd have to have a single drip point that would stay stationary? You know, I guess at the time I didn't really ask the question, and maybe this is also speaking to her why I think it's so important that we have our undergraduates thinking critically. Why did I think the ocean kept moving back and forth? And I don't have a good answer for that. You know, what was the mechanism that did that?
Do you really think that mainstream geologists don't have a mechanism for seas advancing and retreating?
Well, of course, no, absolutely.
You don't think they do?
No, I think they absolutely do.
Okay.
Because that's what I'm saying
You
is,
said you didn't know about the mechanism. There have to
I didn't ask enough questions about the mechanism.
Okay.
I didn't think critically about the mechanism. I guess what I would contend is that absolutely, secular geologists most definitely have an explanation, as do young Earth creationists. And the question is which models better the conditions and what we actually see. And that's where I would, you know, I needed to be more critical about, does this make sense? What is the mechanism here? And can it happen repeatedly? Do we have a good way to explain that? You know, there are a lot of issues, though, that whether we're talking about young Earth geology or we're talking about secular geology, that none of us fully understand, and in both schools would be willing to say, we don't fully understand this. I sat in classes with professors that said, we don't fully understand this. And I say to my students, we don't fully understand this. So that's true across the board.
You made it sound like scientists have no idea what could be the mechanism for that. That's why I asked the question.
Okay. And that's certainly not my intention. I think that there are some amazing, intelligent, and some of them are my mentors and friends. They don't agree with my new position, but that doesn't make them any less my mentor or my friend.
When you're talking about Rid Mountain and how the rock formation shifted, you saw the ripples.
Yep.
Was that a flood connection, or did you mention the mechanism behind that?
To actually turn the quartzite, that's actually not necessarily flood. Other than that, the igneous intrusions, I believe, are connected to the rifting that's going on as part of the fountains of the Great Deep. Actually, the rotation of the quartz, that is the same as a secular explanation. The only difference between my explanation and the secular explanation in that particular rotation feature is the time it would have taken and when it happened.
Yeah, I got a question on Lake Superior, the perimeter around the lake, you got Wisconsin, Minnesota, and everything came out of the rift in the middle, right?
Right.
So.
It kind of makes a curve.
Are things similar then? I mean, the features look different. You know, sometimes you see sheer cliffs and others wash it, but are the materials geology-wise the same? Wisconsin as Minnesota, the same materials?
Coming out of the rift itself.
Well, what are there now? You know, the result of what was coming out.
Yeah, the entire rift would be this system of basalt and rhyolite, but you can't see it everywhere. So the further you get from that center of the rift in the center of Lake Superior, the more it's buried by either flood sediment or ice age sediment. So like it comes down, you know, it actually curves all the way into Kansas. But you can't see it like in the center of Minnesota because it's buried. But you can find it on a, you know, if you had a magnetometer, you could go out and you could locate where the rift is and things like that. It's most visible in the Lake Superior basin itself. Now the actual shape, the final outline of Lake Superior, that was changed by glaciers. So the shoreline, for example, but the depression for Lake Superior was there before the Ice Age. Of course, then it kind of got carved out and shaped by as the glaciers came through that area.
It seems as though there's some very high quality limestones around the Fond du Lac area, hard, dense limestones. You get into Minnesota and it's a softer Mankato type of stone, yellowstone. It's much softer and less durable. Is there a reason for that, or have you got a sense of what occurred there that made it different?
Made it different. Well, not knowing the age of the Mankato limestones, I'm I'm not sure that I would have a great explanation for you, other than sometimes it just has to do with the deposition. So that might be a later sequence. And again, now here I'm gonna be honest, I've only lived in Minnesota for a short time, so I don't even know for sure. Mankato is south?
Yeah,
All right.
it's a yellow limestone, and it just is, it's marginal.
Yeah. And sometimes too, if you have more water present, you're gonna get more things dissolving out of it. So it depends. I would say, you know, there just might be a difference in the depositional environment, but I wouldn't feel comfortable speaking to it too much, not knowing what the Mankato limestone exactly, where it falls.
Okay, versus, say Fond du Lac, Wisconsin, that part of the world is, and it's known for some marvelous.
Yeah, yeah, and that would be similar to the limestones you see like in Peninsula Park in the UP. It kind of goes up around that way.
Door County.
The Niagara Escarpment, and that's yeah.
How do you explain the dells?
There was
Dells and dells.
yeah. Well, we talked about that at dinner. There was a picture of the dells, and I said I didn't include the dells because everybody just goes to the water parks. But there you have some sandstones and things. You have some flood sediments, and I think as you kind of much like Perrot, some of those channels are originally going to form during retreating floodwaters, but then when you have the meltwaters from the glaciers and some of those glacial lakes draining, that's where you're going to get kind of the final definition and features for some of those drainage channels. That one's in Mosinee, Wisconsin. It's not accessible to the public, so it's actually in a working quarry. They were quarrying and found it. They're protecting it, and you can ask permission. Some geologists have asked permission to go in and photograph it and things, but it's not like an open to the public site. So it's actually in a quarry that's still operating today in Mosinee, which is, if you know where Wausau is, right in the center of the state of Wisconsin. I just think it's amazing you can fossilize a jellyfish. I don't know.
In your fossil graveyard you mentioned at Peninsula, are there fossils of modern fish or sea turtles or whales?
In that one, no. That one is primarily brachiopods, crinoid stems,
Why not?
those sorts of
Why
things.
wouldn't there be? Since they were all living together.
At the same time.
They were.
All right. Well, the fossil record does show progression. This has to do with the stages of inundation onto the continent. So that's similar to, if we're in an early stage, the Sauk mega sequence, we have some of those initial tsunamis coming onto the continent. Those are going to be some of the reefs offshore, some of the first things deposited on land. You're going to get the larger fish and things coming in later. Similar to the fact that we have dinosaurs and whales in all the deposits that have dinosaurs. You know, that's one of the fallacies too, is that when we get to things like mammals, we only have mammals. Well, that's not true. We have fish and whales and everything mixed together. So as the floodwaters are going to cover the entire continent, we're going to get a bigger jumble of and bigger variety of both sea life, as you're asking, and land animals that are going to start to get swept in then along with the sea life. So there's some progression there as the floodwaters come on. If you want a great resource for that, I get that sense, but that's all right. For the rest of you, if you want a great resource, Dr. Clary has some great work on how those fossil depositions in the sedimentary layers line up and why they are the order that they're in. Dr. Clary, C-L-A-R-E-Y, the Institute for Creation Research. They've done some things because he's the one that's doing kind of the continental-wide sediment, and that's one of the things he's looked at is the fossil record and how they line up. Because that again is one of the things that is used to promote evolution. Well, we have, you know, early, which is my guess is the impetus behind the question. You know, we have these kind of early simple life forms. And then we progressively get more complex as we go up the chain. And the explanation could also be that we just have pulses coming in from tsunamis and different timing of these fossils being deposited. And regardless, we have marine fossils with land fossils, and we still have to explain the Cambrian explosion. No matter what, fossils just suddenly appear, all kinds of life, fully formed. So that's my guess, right?
Is that the kind of fossils that are in the state park?
This is going to be, this is the crinoid stems. I don't know if I can go back to the picture. Crinoid stems, brachiopods, they're going to look like little clams. You know, crinoid stems are a plant.
Is that considered the same kind of fossils that would have been
In the Cambrian explosion, well, those are going to be some of the early arrivals in the Cambrian record. But so you're talking about the when I'm talking about the Sauk megasequence, I'm saying there's about 6 of these continent-wide. Sauk is the first. So this is going to be early flood. So when we talk young Earth, we don't really talk about Cambrian and things. When I say Cambrian explosion, that would be a secular term. So the Cambrian explosion is where they, in the old Earth framework, would put that Cambrian boundary. All of a sudden, life appears. In many ways, fully formed, in all different, not a gradual tree of life kind of progression. And so that's one of the challenges, is how do you explain an explosion of life at one level. That's a little bit different than the reef structure at Peninsula Point. There you're going to find mostly what they would say a reef was deposited there. So an early reef, early in the flood.
So is Wisconsin Dells, is that the sediments there, is that like from the Sauk megasequence?
When you start to get further down in Wisconsin, you will start to get some of the other sequences beyond the Sauk megasequence. So if you remember, I talked about everything had to go around the rift. So you sort of have this thickening away from the rift. So they're the thinnest right at the rift, and they get thicker. So you will get some other megasequences as you move farther and farther from the rift. Which ones, and this is when I actually wrote the book, and it's been a while since I actually did this particular work. I didn't have where the sequence boundaries were throughout the state of Wisconsin. But I would be willing to bet that if I went back now with some of the things that have been done at ICR with the megasequences, now I could go back and write in those lines, because there's some maps now that just didn't exist when I did this work. So that might be an interesting challenge to go back and kind of figure out exactly where the dells fit. But at the time I wrote it, I didn't have that. And I'm not sure if he's published, some of you might know, I'm not sure if that's all published yet or not either, some of the maps with some of that.
And you also said the larger the cross bedding or something, what was it, the faster the water, or there was a lot of cross bedding there?
There is a lot of cross bedding, yeah, and large cross beds, you know, you're kind of pushing a sand grain up and it's going off the other side, so the larger the cross bed, you've got to have some power to move that. And the cross beds do, for example, in pictured rocks, if you go to the Chapel Hill, you're going to have larger cross beds that do get smaller when you get into the minor castle, so the water was getting deeper, probably the velocity at the base was changing. The changing velocities will also give you ripple marks, they'll give you bedding planes. So Berhalt, who I quoted in here, he has a really great graph that shows what the velocity has to be at what depth to form each feature. And it's changing. That's one of the interesting things about Grand Canyon too, is the size of the cross beds, you know, indicate some really extremely rapid currents in those floodwaters.
A question about, have you ever been to Superior Falls in between Michigan and Wisconsin?
I have not been to Superior Falls. Michigan and Wisconsin, like by St. Ignace, that area?
Yeah, so the river that actually flows is the border between Michigan and Wisconsin, but there's a waterfall over there. And some of the rock formations kind of around that waterfall, they rise up about 100 feet from the riverbed or so, but some of, I was asking because some of the rock layers look like they're totally vertical. Like, you know, you normally get the layering, but it's
right.
Totally upright.
Well, in that part, because the rift does curve around and go back down into Michigan, if you remember from the map, it makes kind of that U shape, so those very well could be rift sediments, and then it would make sense in the same way that as that rift down dropped, you'd get almost those vertical volcanics rather than a horizontal
Okay.
orientation on those. Yeah.
Do you have any insight that you would like to give us about Hawaii right now?
You want to know how Hawaii forms?
Well, just about the volcanoes and I mean, I
Oh, because it's erupting right now. Yeah, that's right, Kilauea. Well, Hawaii is a hot spot. So it's in the middle of a plate. So there's just this mantle plume that just keeps feeding the Hawaiian volcanoes. And as the plate moves, you know, a new spot moves over that hot spot and it erupts. It's interesting that it's getting so active. I think that there's been some other things that have gotten more active in recent times. I wouldn't speculate on the reason for it.